Welcome you all. I am Dr. Jahan, Associate Professor, Electronics and Communication Department from Rohini College of Engineering and Technology, Kanyakumari. So this video I have discussed about ADA wireless sensor networks. Transport layer protocol. The transport layer protocols provides end-to-end segment transportation where messages are segmented into a chain of segments at the source and are reassembled back into the original message at the destination node. Transport protocols are used to mitigate congestion, reduce packet loss, provide fairness in bandwidth allocation, guarantee end-to-end reliability. Examples of traditional transfer layer protocol, transport control protocol, user datagram protocol, sequence packet exchange protocol. Network link, Microsoft's approach to implementing IPS SPS. Challenges and issues in transfer layer protocol. Wireless sensor networks should be designed with an eye to energy conservation, congestion control, and reliability in data disseminations, security, and management. The congestion control may involve only the transport layer, but energy conservation may be related to the physical data link, network, and perhaps all other high layers. Designing a new transport layer protocol for wireless sensor networks should consider the following issues. Induced traffic. Unlike wired networks, ad hoc wireless networks utilize multi-hop radio relaying. A link level transmission affects the neighbor nodes of both the sender and receiver of the link. In a path having multiple links, transmission at a particular link affects one upstream link and one downstream link. This traffic at any given link or path due to the traffic through neighboring links or paths in referred to as induced traffic. This, this is due to the broadcast nature of the channel and the location dependent contention on the channel. This induced traffic affects the throughput achieved by the transport layer protocol. Induced throughput unfairness. This refers to the throughput unfairness at the transport layer due to the throughput delay unfairness existing at the lower layers such as the network and MAC layers. Separation of congestion control, reliability and flow control. The transport layer flow can experience congestion with just one intermediate link under congestion. Hence, in networks such as ad hoc wireless networks, the performance of the transport layer may be improved if these are separately handled. While separating these most important objective to be considered is the minimization of the additional control overhead generated by them. Power and bandwidth constraints. Nodes in the ad hoc wireless networks face resources constraints, including the two most important resources, power source and bandwidth. The performance of a transport layer protocol is significantly affected by these constraints. Misinterpretations of congestion. Traditional mechanisms for directing congestion in networks such as packet loss and transmission timeout are not suitable for directing the network congestion in ADA wireless networks. This is because the high error rates of wireless channel location dependent contention, hidden terminal problem, packet collisions in the network, path breaks due to mobility of nodes, and node failure due to drained battery can also lead to packet loss in ad hoc wireless networks. Hence, interpretation of network congestion as used in traditional networks is not appropriate in ad hoc wireless networks. Completely decoupled transport layer. Another challenges faced by a transport layer protocol is the interaction with the lower layers. Wire network transport layer protocols are almost completely decoupled from the lower layers. And in ad hoc wireless network, the cross-layer interaction between the transport layer and other layers such as the network layer and the MAC layer is important for the transport layer to adapt to the changing network environment. Dynamic topology. Some of the deployment scenarios of ad hoc wireless networks can lead to frequent path breaks, partitioning, and remerging of networks and highly in re-established paths. Hence, the performance of a transport layer protocol is significantly affected by the rapid changes in the network topology. Generally, transport control protocols designed include two main functions: congestion control and loss recovery. The design transport protocols for wireless sensor networks should consider the following factors: perform congestion control and reliable delivery of data. Since most data are from the sensor node to the sink, congestion might occur around the sink. Wireless sensor network need a mechanism for packet loss recovery, such as acknowledges and selective acknowledges used in TCP. It may be more effective to use a hop-by-hop approach for congestion control and loss recovery, since it may reduce packet loss and therefore conserve energy. The hope by hope mechanism can also lower the buffer requirements at the intermediate nodes. Transfer protocols for wireless sensor networks should simplify the initial connection establishment process or use a connectionless protocol to speed up the connection process, improve throughput, and lower transmission delay. Transfer protocols for wireless sensor networks should packet loss as much as possible, since loss translates to energy waste. To avoid packet loss, the transport protocol should be used in active congestion control at the cost of slightly slower link utilization. ECC trigger congestion avoidance before congestion actually occurs. The transport control protocol should guarantee fairness for a variety of sensor nodes. If possible, a transfer protocol should be designed with a cross-layer optimization. For example, if a routing algorithm informs the transfer protocol of route failure, the protocol will be able to reduce that packet loss is not from congestion but from route failure. In this case, the sender may maintain its current